Hello, and so this is just continuing exactly where we left off in the previous video. So please make sure you watch the previous video before this one. Yeah, so we are at this point and we can go ahead and expand this. If we expand this, we have ks plus ak all over, we have s squared plus 2as plus a squared plus omega squared. Good, so we're here. Now we see a small, big problem. It's a very small problem, but it's very big. Our denominator is fine. Denominator looks very much like this, but our numerator is not fine because we have two terms in the numerator. Okay, we have two terms in the numerator and we have just one term in the numerator. How do we deal with this? So why not let's play with what we have here, our actual system. We have, so maybe let me just work with this term alone so I don't have to keep on writing this a bunch of times. Minus 1 over 4s over s squared plus s plus 4. That's what we'll be working with now. Now, this looks like k, which is fine. That's the ks. But we have an ak that we have not dealt with, okay? And in fact, we shouldn't just assume that this is k, to be honest. The best place to start from is always from this denominator, starting from your a. Okay, always start from your a. A is the best place to start from because if you start from your k and it turns out that it doesn't sync up with a, it could mess things up for you. Let me draw this down. So let's start by a. We can say that our a is equal to 1 based on what we have here. Your a is simply equal to 1. Okay, so if a is equal to 1, then this whole expression now becomes, so let's say let a is equal to 1. If a is equal to 1, this whole expression becomes ks plus k all over s squared plus 2. Oh no, sorry, my a cannot be equal to 1. A has to be half. Okay, if a is equal to 1/2, then 2a will be equal to 1. Okay, so if my a is equal to 1/2, then that'll be ks plus k over 2. That's ks plus ak. Ks plus k over 2 is equal to s plus, now this will no longer be, okay, let's just get this out of there. This will no longer be 2. Okay, instead this will be now s squared plus s, which so far is beautiful for us. Then plus, we're supposed to have an a squared plus omega squared. A squared in this case is 1 over 2 squared plus omega squared. This makes things a whole lot more interesting. Okay, so this is equal to ks plus k over 2 over s squared plus s plus 1 over 4 plus omega squared, which is actually very, very interesting. Why is this very interesting? Well, it's interesting because it's different from what we have over here. Okay, it's quite different from what we have over here. It seems that based on what we have here, our k might be equal to negative 1 over 4, but that doesn't quite work out for us. So if k is minus 1 over 4, then how do we deal with this term over here, k over 2? Now, let me make a suggestion. Let's try to make this term here as close as possible to this term over here. By the way, from what we have over here, it makes sense that our 4 is equal to omega squared plus 1 over 4. So we can compute what omega is from this. That will be omega will be equal to this 1 over 4. 4 minus 1 over 4 will be equal to what? That will be 3 whole number 3 over 4. That's the same thing as saying 15 over 4. Okay, so that will be the square root of 15 over 4. Okay, so our omega is square root of 15 over 4. That part is simple. That's not too much of a trouble. The problem is the numerator. How do we deal with the numerator? Let's assume that our k is equal to minus 1 over 4. So let me write that down somewhere. Let k be equal to minus 1 over 4. Okay, if your k is equal to minus 1 over 4, then this expression will now come down and be equal to minus 1 over 4s, which is good, plus this. So now this will now be a negative. It will no longer be plus. It will now be minus 1 over 4 divided by 2 minus 1 over 8. All of this divided by, let's scroll down a little more, all of this divided by s squared plus s plus, I hope you don't mind if I just go ahead and write 4 over here, because I've made my omega equal to square root of 15 over 4, in which case this just pans out to be 4. Okay, so this is now looking relatively beautiful, but we still have the issue of this term here, minus 1 over 8. That is different from what we have in our expression over here. Okay, so that minus 1 over 8, how do we deal with it? So let me go ahead and rewrite this expression that we have here. So let me scroll up a little so that it's all in focus. So minus 1 over 4s over s squared plus 4. It makes sense that this is the same thing as minus 1 over 4s minus 1 over 8, okay, because that's what we have over here. That's beautiful for us. But let me add something, plus 1 over 8. Now, this numerator is exactly equal to what we had over here. And then we have s squared plus 4 plus s plus 4. Now, this is exactly equal to that. And this is looking quite good. Now, simple mathematics, you know this is minus 1 over 4s minus 1 over 8 divided by s squared plus s plus 4 plus 1 over 8 over s squared plus s plus 4. Have we made our lives better or have we made it worse? Well, let's look at what we have. This expression here, minus 1 over 4s minus 1 over 8 divided by s squared plus s plus 4, is exactly what we have here. We know the inverse Laplace transform of that. Now we're left with this term over here. So we have to find the inverse Laplace transform of this. Can we find the inverse Laplace transform of this? And I dare say, yes, we can. So let's say we want to find the inverse Laplace transform. Our new task is to find the inverse Laplace transform of 1 over 8 over s squared plus s plus 4. Okay, is this possible? We will not just end up with a problem like we just had right now. Well, let's find out. Let's say now in this case, we're not thinking cosine, we're thinking sine, because thinking sine because we have no s in the numerator, so we're thinking sine in this case. So let's think about the Laplace transform of a sine term. If you are looking for a Laplace transform of a sine term, again, I would suggest have a constant multiplied by e to the power minus at. Okay, so let me call this, let me not use k and let me not use a, so we don't confuse it with other things that we've used before. Let me say p e to the power of minus bt sine of omega to t. If we find the Laplace transform of this, this will give us p, which is our constant, multiplied by omega 2 in this case, all over s plus b squared plus omega 2 squared. Expand this gives us p omega 2 in our numerator divided by s squared plus 2 bs plus b squared plus omega 2 squared plus omega 2 squared. Start from this term here. 2b is equal to what you have over here. That means that your b is equal to 1 over 2. If b is equal to 1 over 2, you can put it into this term here. Now, I could have told you straight up that your omega will be the same frequency you have here. Your b will exactly be the same thing that you had here for a. But let me just go ahead and do that computation. You end up with your omega 2 being also equal to square root of 15 over 4. It's because it's the same frequency that you're working at. The sinusoidal term, whether it's cosine or sine, will apparently be at the same term. So all we're left with now is our p. We're left with computation of p. We know that 1 over 8 is equal to p omega 2. Omega 2 is this term over here. So our p comes out to be, I will not try to simplify this. Our p comes out to be 1 over 8 square root of 4 over 15. But I could try to simplify this, so that will give me 1 over So this will give me 1 over 2, that'll be 4 root 15. Okay, so I hope that is correct. I hope I didn't make any mistake in that. Now we have all the terms. We have the inverse Laplace transform of this. We have the inverse Laplace transform of this other term here. And the very first term that we didn't even bother about, we know the inverse Laplace transform of that. So after a long work, let's now find the inverse Laplace transform of our expression. Where's our original expression? Okay, of our original expression. Now let's find the inverse Laplace transform of this. So let's go ahead and just copy this term, if it will allow me to do that. Let's go ahead, copy that term, and I hope I can paste that down here without going through too much trouble. Okay, so now we want to find this inverse Laplace transform of this. Where are you? Okay, I'm sorry, we just want to remove that line. Yeah. Okay, so now we can write out our inverse Laplace transform of this entire thing. Remember this entire thing, let's first of all write out everything that it was equal to, so that we can now write out the Laplace transforms without any errors. Okay, first it is, okay, first of all, let me just make sure that you know that this was 0. So let's copy this first term here. So the first term we have is this term over here. I'll put that down here. So that's the first term. The second term is what we have. Oh, in fact, okay, so I could just write out these two terms. I'll copy these two terms together. Those are the last two terms that you have in there. Okay, so it's equal to this. So the inverse Laplace transform is the inverse Laplace transform. Let's try to squeeze that in here. Inverse Laplace transform of this entire thing over here. Okay, and now this we can easily work with because we know the various terms. So that is equal to 1 over 4 e to the power of minus t. That part is simple. Plus, now we need all the various terms that we had over here. What was our k? Our k was minus 1 over 4. So we have minus 1 over 4, e to the power of, and our a, which actually turns out to be exactly the same thing as our b, is 1 over 2. So that's minus 1 over 2t. Cosine of the frequency is the same, square root of 15 over 4 multiplied by t. And then we now have our sine function here. In this case, our p is equal to, so plus 1 over 4 root 15 times the sine of the square root of 15 over 4 multiplied by t. Okay, so this is our solution of this is the inverse Laplace transform of this function. This long expression here is the inverse Laplace transform of this function. Now this expression is actually just 3 parts. If you want, it is actually just 2 parts. The first part is an exponential function, 1 over 4 e to the power of minus t. And the second part is comprises 2 different terms. One is your exponentially decaying cosine curve. The other is an exponentially, oh, sorry, I left out the exponential here. So sorry about that, minus 1 over 2t. Okay, the second is an exponentially decaying sine curve. Both are sinusoidal curves, so that really all you have is an exponentially decaying sinusoidal curve. The amplitudes of these are somewhat different, and this is what you have. Now, it turns out that if you actually worked with the complex numbers right from the get-go, if you had worked with the complex numbers and gone ahead to just try to find your, if you had worked with all these complex numbers, try to find our K2, find our K3, we would have arrived at the same answer, but you probably would have pulled out your hair a little bit. Or, well, arguably, for those who love working with complex numbers, actually, you probably have just enjoyed working with that perfectly well. But this is the inverse Laplace transform of the system. Now, looking at this and looking at how we solve this, I believe you can go ahead and find the solution to this. Remember that this is where where the whole issue started from. To find the inverse Laplace transform, I believe it is 3 over s squared into s squared plus 2s plus 7. This was the question we started with. Now you have everything in your arsenal to find the solution to this. And I would encourage you, go ahead and find the solution to this. See you in the next video.